you so much. I'm actually honored to be here for such a broad audience, because I'm a physicist, but I anticipated that you were quite broad, so don't be too frightened by that. So I will be talking about invariant mathematical structures, and I will explain what I mean by that, because that is kind of key to the activity that I'm involved in. And the focus in terms of oceanography is dynamics of oceanic eddies, so monopolar vortices. I will also say a little bit about the relevance of that. And angular momentum dynamics, which is quite a broad concept in physics. So my background is in physics. I'm from the Netherlands. I will tell a little bit more about that tomorrow, but the Netherlands is all about water and water management. And for today, that provides a background. More specifically, I'm from Delft University of Technology, but that university has a lot of faculties that are involved in water activities. So we have a special faculty for maritime engineering. There's geo and civil engineering. But I myself, is there a pointer? Okay, I'm in the mathematics department. Okay, that's of relevance, of course, for my research theme. I have to approach my research from the point of view of applied mathematics. And I've defined it as this. My research focus in daily life at the university is research into application or applicability of mathematics for conceptual understanding in a broad set of physics, but I focus on processes in the oceans because I have a background of my PhD, which was in geophysical fluid dynamics and especially in ocean monopolar vortex dynamics. So that will be the focus of today, in view of the topic of the conference, of course. I will be talking about understanding by application of mathematics to get a better understanding of the so-called intrinsic drift of oceanic monopolar vortices. I will explain in a minute what exactly is meant by that. First of all, these mesoscale oceanic monopoles. These are swirling water masses that are ubiquitous in the oceans. And back in the 1990s, when I did my PhD research on those, they were most recognized as shed-off strong vortex motions, so swirling water masses that were shed off by the western boundary currents, such as the Gulf Stream over here, that breaks off kind of a monopolar moving swirling water mass, which is called a vortex. Here's one in the Kuroshio near Japan, and the most beautiful examples are shed off by the Agulhas current down the tip of South Africa here. So you have these rings. So back then we did research in that just out of curiosity. But last year in Science, the Science journal actually, in June there was a publication by Zhang and Q. And that nowadays we know from satellite observations that these features are actually much more ubiquitous in the ocean and much more playing a role also in a zonal net transport. It was suggested that if these vortices would indeed contain a water mass that they could transport, that is trapped in it, so that they transport it over large distances, then the integrated total transport that is induced by that is comparable to large-scale wind and thermal-driven circulations or total budget of transport by the Gulf Stream, for example. So this might be quite important in terms of transport budgets for the global ocean, provided that indeed the water mass that is trapped in the monopole is indeed transported by it. And that Science publication ends with a big question mark about that item. To what extent actually do these vortices represent a transport mechanism? So that is why this is still an active and then actually quite relevant topic of research in physical oceanography, so dynamical oceanography. This is again a classic observation focusing on the property of drift, so the intrinsic ability of these phenomena to actually do transport. That is because they intrinsically have the tendency to move by themselves westward. One of the intriguing things is that they do so irrespective of their sense of rotation, the spin. So either whether they go clockwise or anti-clockwise, so either if they are cyclones or anti-cyclones, they always go to the west. And a classical experiment by the Soviets back in the 1970s actually directly demonstrated that these vortices have an intrinsic tendency to drift westwards. So this experiment detected the vortices in the Atlantic by moored current meters. And in that way they were actually able to also measure the background current, the mean background current. And if you subtract the observed transport of the vortices, so the observed motion, and you subtract of that the background current, you get a difference. So that means they move with respect to the background current by a mean velocity at that altitude, geographical altitude, of about 1 to 6 centimeters per second. So the picture is this. You have a swirling water mass that is potentially trapped in time in terms of the vortex, and the vortex as a whole moves westward. So there you have this potential transport mechanism. And one of the questions of the central question at that time of a lot of the research that was going on was why do they do that? What is actually the reason why they go westward? And then going back to my research focus, that's my research focus, to understand why things happen, why things operate in the way they do. And I try to enlighten that by applying mathematical methods. So a little bit about my scientific method. I'm in applied mathematics. The group is called mathematical physics. And okay, I envision myself to be in the middle of all this. Where's my point? Okay. So I view mathematics as the science of structures as such. So a real pure mathematician is not interested in whether or not the structures that he studies apply in the real world. He's just interested in the logic of it, right? So that's mathematics. And on the other hand, we have the real world where we have our observations. And I imagine myself to be in the middle of that. I'm neither a pure mathematician. I'm also not going out in the sea. I use this, but I try to build a bridge. So I'm standing with one foot in this world, one foot in the other, and try to build a bridge. And hopefully that helps to understand. So I try to recognize structures and clarify them by really clearly defining them in a mathematical way and use mathematics to analyze them and calculate their implications. So we move back and forth between these two worlds. Now the movie that we just showed here plays a central role in the understanding of this intrinsic drift phenomenon, so I will be talking about it quite some more. But okay, so it's all about mathematical structures, and for the sake of this presentation I've built kind of a hierarchy that is numbered. So I'm not numbering the slides, but this is number 1, mathematical structures 1, is this slide showing, let's say, one level in the hierarchy of mathematical structures as I envision my activity in this field. So the first level of mathematical structures are the directly observable ones. So in practice you measure distributions of temperatures or densities in the ocean, and here's a plot of a density back from the 1980s, a classical one, of the observation of a oceanic cyclone, or anticyclone over here. So anticyclone is a high pressure field, and you see this bulging density profile. Now, in terms of mathematics, this is a fairly basic mathematical structure. It's a scalar field, we call it. It's just a functional dependence. How does density in this case depend on position, right? And a somewhat more advanced example is over here, the velocity distribution. How does velocity depend on two-dimensional position in space? So you might not even recognize these as mathematical structures because they are so basic and so familiar. But yet they are. And then there's a second higher level. I would say those are the laws of nature, as we call them in physics. And they typically come in the form of differential equations, mathematically speaking. And that's kind of bookkeeping. So a mathematical equation is a kind of a bookkeeping of balances. For example, we have this conservation law of mass. So a fluid might be compressed, but there's a limit to that. It must, if it is compressed, it must flow in such a way that at the end of the day, all the mass that is involved is conserved, right? So you can push the mass by the fluid motion into a smaller volume, but at the end of the day, the volume must contain the same mass as it did before the larger volume. So it's bookkeeping. And we do it in 3 dimensions, and we do it as function of time, and then you end up with what we call differential equations. And that actually dictates a lot of activity in mathematics. So for many mathematicians, these differential equations are kind of puzzles. Once you have them, you start solving them. That is, study the consequences of those differential equations. So a lot of mathematics is about solving differential equations. Now, in terms of the philosophy of science, you can view that as studying the consequences of these laws of nature, and then in the end you can compare the outcome of your mathematical solution to what you observe in the real world. And then think back to the classical philosophy of science, for example, as published by Karl Popper, the great philosopher. This is something like testing your laws of nature, right? Solving the differential equations, and look how they fit in the end of the day, the real world. So that's the second level, solving differential equations and the mathematics of solving them. We will come back to that later. My own core activity, I would say, and the core result that I'm going to present at the end of this presentation is at a little bit deeper level. I think it is important to mention that so that you can recognize it and appreciate it. I'm interested in looking at invariance. Let's take one step back. When you solve a differential equation and you produce a function, then in practice it will turn out that these functions change when I use a different coordinate system. And I have a small movie of that to illustrate the idea. So let's have a picture of the Earth. So here's the Earth rotating about its axis. And here's a geographical coordinate system. But nothing stops me from using another coordinate system. So actually in this movie, it's not the Earth that is tilting, it's only the coordinate system. So in practice, you have choice about which coordinate system you use. And then if you think back about these fields, these functions that describe temperature distributions of the ocean, for example, as a function of position, if you do that as a function of coordinates and then you change the coordinates, your functions will change, right? So what you're really interested in is not those functions, but the real world that is behind it. So I have another example here on the right that kind of gives a hint of what I mean if you look at it. So again, we have the Earth, and then here's flashes of vector fields, and you see still the coordinate system change, but the vector fields do not change along with them. So that's the notion of an invariant, and that has kind of the flavor of something that is real, that really exists independent, that is behind the real mathematical description. So I have another example of that The next slide. If you compare the two movies right here, again I have a sphere and I have a geographical coordinate system that changes and a vector field, but this vector field is attached to it, right? And I compare that to what happens in the other movie. Again, I have a coordinate system that changes, but this vector field does not change along. The description of it changes a little bit because I describe the field, but still this field describes the rotation of the sphere of the planet about its polar axis, while this field appears to describe a rotation of the coordinate system. So now you start, if you compare these two movies, you start to realize that there's something more to the description than meets the eye in the first place. So that's the kind of mathematics that I'm involved in. Mathematics of invariance, the mathematics of looking what is the real world behind the descriptions that we generate in the more basic kind of mathematical approaches of solving differential equations as such. Now, once you get involved in that, a very classical example of an invariant is the shape of a sphere. The shape, and that's the notion of symmetry. So I have again this movie that we looked at before, but let's look at it again. So I have a sphere and I rotate it about an axis, and I can choose that axis in many different ways, so that means I can rotate this sphere in many different ways, but whatever you do, this shape really doesn't change. It looks the same, whatever I do to it. Now that's the notion of symmetry, which is a very deep and very broadly applied notion in physics. So it's the basis of most of atomic physics, of quantum mechanics of atoms. It's much applied in classical mechanics as well. It is the basic of the theory of the spinning top, solid body mechanics. And one of the driving ideas behind my own PhD work was, can we apply this in ocean dynamics as well? Now, the basic mathematics that is behind this notion, the analysis of the symmetry of a sphere, which is of course directly applicable to the symmetry of the Earth, which is very well approximated by a sphere, is the mathematics of groups. So that goes back to the mathematician Sophus Lee, who was halfway the 19th century and studied this, and he discovered the notion of a so-called group, which is now called after him a Lie group. And the basic discoveries are this. It turns out that can be proved mathematically, and I cannot possibly go into the details, but I will tell you the result. So we saw there's an infinite sea of possible rotation operations, but it turns out that I need only 3 building blocks that are shown right here. And actually you're free to choose them, but I've chosen 3 building blocks. The great discovery of Lie was that I can produce all possible rotations from a weighted sum of these 3. So the addition is a mathematical operation that is defined for these fields. I can even make it a weighted sum, so I can multiply them by a scalar, by a number, and then add them up. So that's called linear combination. And then it can be proven that all the possible rotations can be generated from only these 3. That means the number 3 is fundamental to the group of rotations. You have 3 independent building blocks. And I will come back to the implications of that in a minute. Now, furthermore, this is a very beautiful, mathematically a very beautiful closed structure, because Lie discovered there's also something like a product. In essence, it's like this. I could observe that how does this field change if I travel about a sphere along this vector field. So I follow these arrows and travel about in this way about the sphere, and then look at this field and observe how it changes. It will change. That's called the derivative. And then I can turn the other way around. I can travel this way about the sphere and look at this field, how that changes, and then compute the difference of those changes That's what this little bracket is denoting. And then, surprising or not, it turns out that that construct delivers exactly the third element. Now that's a fingerprint. So there's a table of multiplication in the sense of mathematics. Mathematics like this very much because it gives a closed structure. You have 3 building blocks. You can multiply them, and you get a table of multiplication. 1 times 2 gives -3 in this construct. That's why this is called the Lie algebra. So you can add and you can multiply. So we have an algebra. It gives a closed structure. So that's mathematically very beautiful. And I cannot go into the details of that, but the mechanics of ocean vortices, in that mechanics, actually this product plays a very important role. For today, I will leave it at that statement. Okay, there's more. So we have this product multiplying these vector fields by one another. There's also what is called an inner product. That's actually an extension compared to the basic notion of a Lie group, but it is essential for the application to ocean dynamics. Inner product is a mathematical concept that is understandable in terms of projection. So as I said, I can make linear combination of these vector fields to produce any rotation. That can be described by a diagram like this. So these elements correspond to 3 perpendicular axes in a 3-dimensional space, 1, 2, 3, and then an arbitrary rotation can be depicted in this plot by an arbitrary arrow in this space. And then this arrow has 3 components. You can project this arrow on each of the 3 axes of this abstract mathematical space. The fact that that is possible corresponds to the existence of this extra construct, which is called the inner product. Now the key to the application of all this to ocean dynamics is that this inner product not only is applicable to fields that are elements of this group of rotations, no, it is actually applicable to any vector field on the sphere. So in an abstract sense, I've depicted it over here. So if I have these water bubbles inside this big arrow, so this kind of is an abstract indication of a flow of water over planet Earth, right? Over all of the oceanic environment. And the message is that I can, because of the existence of this inner product, I can project this global velocity field onto the 3 elements of the group of rotations. That means any vector field, any current system in the ocean has 3 components in terms of this group. And I can also, but that's a lot of work, so it is just work. It is work you can in fact project all of the classical mechanics, the Newtonian mechanics, onto this group. So I can construct the dynamics of the 3 components of a general velocity field onto this group. Now, I could not possibly explain that in a presentation of 20 minutes, but what you can recognize, I get 3 equations, right? Because the group is 3-dimensional and I have 3 building blocks. I project a general velocity field on these 3 blocks, and then I construct the dynamics of it. How do these components evolve in time as a function of time and as a function of one another? So I get 3 coupled equations. So far we were on 3rd level of mathematics, right? In the hierarchy that I use for this presentation. But now we are back on the 2nd level again, because I just have 3 3 ordinary differential equations. These dots indicate the derivative with respect to time. So I have 3 ordinary differential equations describing the position of my coordinate system. Lambda is the latitude, theta is the altitude, and then there's a 3rd degree of freedom left, that is the intensity of the vortex. So this is again 2nd level mathematics, And it happens to be, because this rotation group is a group of symmetries, and because you can show that it is three-dimensional indeed, that these three equations that I have produced are actually form a well-defined closed system. That means you can just apply the usual procedures of solving differential equations to this. And here's the result. This is just a matter of typing it in your favorite computer program, press the button solve, and you produce these plots. And what it shows is trajectories as predicted by these equations of vortices in the ocean. Parameterized by time. So this is a starting point, and then you can follow it in time. It goes like this. You have this cycloid path, and it depends a little bit on the speed that the vortices have initially. So if you launch them in eastward direction, they will react in a cycloid, and in the end, in a net go westward. There's always also stable trajectories that do not do any oscillation, but just travel steadily westward. And there's also these ones that have this smaller oscillations. And here's the speed. Actually, there's 4 classes of them, depending on whether or not you have a geostrophic balance between the pressure and the velocity. That's the famous Buys-Ballot law that also applies in the atmosphere. You have these low pressure zones or high pressure zones, and the air is just swirling around about it. There's a balance there between the pressure and the velocity. You can apply that also here. And then, depending on whether or not you also take the centrifugal force into account, the balance is a little bit different, but it gives about the same result for the mean speed. So the speed is negative here. It means they always move westward. And then there's cyclones and anticyclones. That's why I have four types here. So all the vortices move westward, and at the altitude, I think this is about 60 degrees north. They go with a speed of about 7 centimeters per second, which is about the right magnitude as it is observed in the oceans. Now, as I said, we could identify this underlying structure as a group of rotations by its fingerprint, by its table of multiplication. And that is very broadly applied in physics. As I said, it is applied in atomic physics as well as in classical mechanics and in solid body mechanics. And everywhere where you have a mechanics that is based on this rotation group, it's always angular momentum dynamics, and it can be represented by vector diagrams. So it's basically a balance of the angular momentum and some torque. Now, it happens to be that in the ocean, the torque is applied by the horizontal component of the force of gravity. Okay, let me summarize. So I just present an inventory of the results, and I've again numbered them 1, 2, 3. So based on this theory, we can reproduce the intrinsic westward drift of oceanic monopoles as they are observed in the ocean. We obtain the right direction. They always go to the west, independent of their sense of rotation, independent of the exact balance of the forces in them. I've done that numerically, so I could produce the graphs that I've just shown you. You can also take analytical result, then you get well-known integrals that, as they were published in the geophysical dynamics literature by investigators like Knopf, Kussmann-Rosset, Nikander. So I can reproduce those with the difference that my result is global. So it is valid on the sphere, and therefore I can decide what westward actually means. And that could not be done before, because all these literature results were done on a tangent plane, which was called a beta plane. And that is not well enough defined to actually predict from those theories what happens in real life if you move on a global scale. The outcome of the analysis that I presented here is that westward means moving along circles of latitude. So it's westward in the normal sense. Yeah, I'm finished. I've demonstrated that it is all implied by classical fluid mechanics projected on this rotation group. And then there's some results at a deeper level. We've identified relevant invariants, symmetry group behind this, shown how these form the building blocks for laws of nature that apply to these phenomena, show how all this implies the vortex drift, and I've actually unified the theory of drift of oceanic vortices with classical rigid body mechanics. So that closes my presentation. I will be happy to shortly address any questions if time allows. Thank you.
I think we have time for one question.
Also possible to treat it in a perturbation-like way. It can also produce analytical approximate solutions. I suggest this is a kind of alternative approach. It's a deeper level, showing the mechanism behind it, showing the deeper reason why things happen as they happen. Which is not over, it doesn't at all become clear if you do a numerical solution, because then you just reproduce the effect. It has no planetary power, I would suggest. Yeah.
Ramses, thank you very much.
Thank you so much.
That's yours.